Have you ever looked back into the early universe and wondered whether something there grew up far too quickly? For a long time, the usual picture in cosmology was much calmer than that. The early universe was expected to be a place of first attempts, not finished achievements. A place where the first small structures were only beginning to gather, where the earliest stars were still simple, where galaxies had only just begun learning how to become galaxies. In that picture, the universe does not rush. It builds slowly, piece by piece, layer by layer. Over immense stretches of time, gravity gathers matter, matter forms structure, and structure gradually becomes the rich cosmic world we know today. But when we finally built a telescope powerful enough to look back into that ancient era with much greater clarity, the story became harder to read in such a comfortable way. The James Webb Space Telescope did not only show us a young universe under construction. In several cases, it showed us systems that seemed surprisingly developed already. Galaxies that looked too bright, too massive, too organized, too mature for a cosmos that was supposed to be in its childhood. And then the mystery deepened. Inside some of those distant systems, astronomers began to see hints of something even more difficult to explain. Not only stars, not only galaxies, but enormous black holes that may already have been active, already feeding, already behaving, less like quiet leftovers and more like engines at the center of a galaxy. Engines that pull matter inward, heat it, and turn that fall into radiation so intense that, in some cases, the central region can rival the light of the galaxy around it. Not just what the most powerful object in the universe is, but how something so powerful could have appeared so early. And to understand that, we need to move carefully. We need to begin with something simple but important. When physicists call something powerful, they are not just talking about size. They are not simply pointing to whatever looks biggest, heaviest, or most frightening in an artist's impression. Because in physics, power has a more precise meaning than that. A huge object can still be quiet. A much smaller one can completely dominate its surroundings. What matters is not only how much energy exists, but how strongly that energy is released, how effectively it is directed, and how deeply it can change the environment around it. So when we ask about the most powerful object in the universe, we are really asking a more interesting question. Which object can do the most, with the greatest intensity, over the greatest consequences? And that question will lead us through some remarkable contenders. Exploding stars, neutron stars, magnetars, gamma-ray bursts, black holes. But it will also lead us toward a deeper puzzle hiding behind them all. How did the early universe produce such extreme objects so quickly? Because if some of these giant black hole engines were already alive in the young cosmos, then the problem is not just that they exist. The problem is timing. The universe may have built something extraordinary before it seems like it should have had enough time to do so. That difference matters more than it may seem at first. Because the universe does not produce just one kind of extreme object. It produces many. A magnetar can hold a magnetic field so intense that even our usual comparisons begin to fail. A supernova can briefly flare with enough visible light to rival an entire galaxy. A gamma-ray burst can release an almost unimaginable blast of energy in a very short time. And a black hole can curve space-time so deeply that beyond a certain boundary, escape is no longer possible. Look at any one of them, and it is easy to think you may already be staring at the winner. But there is another kind of power that feels different from all the rest. Not just a flash, not just a brief catastrophe, not just an extreme field. Something more persistent than that. Something that behaves less like a moment, and more like a machine. Because what if the most powerful object in the universe is not the one that explodes the hardest, but the one that can keep working? The one that draws matter inward, turns falling gas into radiation, stirs and heats its surroundings, and over immense spans of time can help shape the future of an entire galaxy. And that idea leads us toward one of the most remarkable possibilities in modern astronomy. Maybe the strongest candidate is not a black hole sitting alone in darkness. Maybe it is a supermassive black hole while it is feeding, while matter is spiraling inward around it, while that infalling gas becomes hotter, denser, brighter, bright enough, in some cases, to turn the center of a galaxy into one of the most luminous, sustained regions in the cosmos. A black hole by itself does not shine. It is not a star. It has no glowing surface. But the material around it can become extraordinarily hot before it disappears from view. Gas falls inward in a spiral. It compresses. It heats. It radiates. And suddenly, something dark begins to look like the heart of a vast energy engine. You can picture it this way. The black hole is the trap. The swirling disk around it becomes the fire, is less than #0. 5# is greater than, and the falling matter is the fuel being fed into that fire. And once that picture comes into focus, the claim starts to feel much less exaggerated. Because now we are looking at an object that is powerful in several ways at once. Its gravity is overwhelming. Its accretion can release enormous energy. In some systems, it can launch jets across enormous distances. It can also heat or drive away the gas that would otherwise help form future generations of stars. So this is no longer just an object sitting inside a galaxy. Under the right conditions, it becomes part of the force that shapes that galaxy's history. The early universe may have been expected to be smaller, rougher, and less developed than what some observations now seem to show. At the same time, we have begun to see that power in physics is not just about size, but about release, influence, and consequence. And when those two ideas meet, one candidate begins to stand out: the feeding supermassive black hole. Not because it is just dramatic for a moment, but because it can operate like a sustained cosmic engine. Even if we accept that a feeding supermassive black hole may be one of the strongest answers to our title, another question follows almost immediately. How could something like that appear so early? To feel why that question matters, imagine walking into a city that you were told was only a few days old. you would expect dust, scaffolding, bare foundations, steel frames still exposed to the sky. But instead, you find finished towers, lit windows, electricity already running, people living on the upper floors. That is the strange impression these observations create. It is not only that the structures exist, it is that they seem to have arrived too soon. Modern cosmology remains one of the great achievements of science. It explains the expansion of the universe, the large-scale arrangement of galaxies, the ancient afterglow of the early cosmos, and a great deal more. But strong scientific ideas are not weakened by difficult questions. They are sharpened by them. So, if the James Webb Space Telescope is really showing us galaxies and central black holes that matured faster than expected, then two broad possibilities stand before us. One is that some of these early interpretations will become more modest as the data improves and the picture grows clearer. The other is that the young universe may have been able to build large, bright, efficient structures faster than our simplest stories allowed. Either possibility matters, because in both cases, we are pushed to understand the mechanism, not just admire the image. What really happens when matter falls toward a black hole and begins to radiate so intensely? How quickly can a black hole actually grow? What slows that growth down? Could some of the earliest black holes have begun from unusually massive seeds? Could they have fed faster than we once assumed? Or does the larger lesson reach even further, telling us that our picture of the young universe is still missing something important? Because in that distant past, in a cosmos that was supposed to be young and unfinished, there may already have been compact dark objects surrounded by such violent infall, heat, and light that they became some of the greatest engines in nature. Tiny in size at the center, but enormous in consequence. If the early universe was still supposed to be learning how to build galaxies, how did it learn to build something like this? But before we decide what deserves the title of the most powerful object in the universe, we need to slow down and ask a more careful question. What does the word powerful really mean in physics? Because if we do not define that word properly, then the whole discussion starts slipping away from us. One moment, the winner is the biggest explosion. Then, it is the heaviest object. Then it is whatever has the strongest magnetic field. And very quickly, the title stops meaning anything at all. In everyday language, when we call something powerful, we usually mean that it feels large, strong, dangerous, or simply impressive. But physics asks us to be more careful than that. It asks us to separate ideas that our instincts often bundle together. Something can be extremely massive and still remain fairly quiet. Something else can be much smaller and yet release an astonishing amount of energy in a very short time. One object may dominate through gravity, another through magnetism. And sometimes the most consequential object is not the one that wins only one category, but the one that can influence many things at once. So before we decide on any winner, we need to slow down and sort out the categories. Otherwise, the whole question becomes slippery almost immediately. The first confusion is a very simple one. bigger does not automatically mean more powerful. That sounds obvious when you say it calmly, but it is easy to forget. A cloud can spread wider than a mountain and still not have the same force. An ocean is larger than a waterfall, but a waterfall can strike with much greater intensity in one place. In the same way, an object in the universe can be larger or contain more matter overall, without being the strongest engine nature can produce. So let's separate the first two ideas. Mass is not the same thing as power. Mass tells us how much matter an object contains, and in a deeper sense, how strongly it contributes to gravity. A very massive object bends its surroundings more strongly, simply because it carries more gravitational weight. But mass alone does not tell us how active that object is. A huge dark cloud of gas can be enormous and still be relatively quiet. Now compare that with energy. Energy is a broader idea. It is the capacity for motion, heating, radiation, and change. An object can hold energy in many forms. In its mass, in heat, in gravity, in magnetic fields, in rotation. But even here, we still have to be careful. Having a great deal of energy is not the same as being powerful. A battery and a lightning strike make that difference easier to feel. Both involve energy. But the drama is completely different. What matters is not only how much energy exists in total, but how quickly that energy is released, directed, or turned into something observable. In physics, power means the rate at which energy is transferred or released. Not just energy, energy over time. And that small change in wording changes the whole discussion. A system that releases a moderate amount of energy slowly may be less powerful than one that releases a similar amount with extraordinary speed. A brief burst can be tremendously powerful. And a long-lived engine can become powerful in another way, by sustaining its influence over immense stretches of time. Mass tells us how much matter and gravitational presence an object has. Energy tells us how much capacity it has for change, motion, heating, or radiation. Power tells us how quickly that energy is being put to work. And that distinction is going to guide everything that follows. But in astrophysics, the picture still is not complete yet. Because power in the universe is not measured only by how much energy something releases. There are other ways an object can dominate the world around it. Take luminosity, for example. Luminosity is simply the amount of energy an object sends out as radiation each second. In practice, that makes it one of the easiest ways to compare how bright different cosmic objects really are. Stars, supernovae, quasars, and many other systems can all be compared this way. If something is highly luminous, it is pouring energy into space very intensely. But brightness, by itself, still does not tell the whole story. It tells us how much light is being emitted. It does not automatically tell us how strongly that object controls matter, bends spacetime, or changes the future of everything around it. And that is where gravity enters in a deeper way. A black hole is perhaps the clearest reminder that brightness cannot be the only measure of importance. Left by itself, a black hole can be almost completely dark. It does not shine like a star, because once light passes too far inward, it cannot return. And yet the object can still dominate an entire region through gravity alone. It can redirect orbits. It can pull gas into spirals. It can reorganize the motion of everything nearby. In modern physics, gravity is not really thought of as an invisible rope pulling through empty space in the old simple way. It is better understood as the shape of spacetime itself. Massive, compact objects bend that geometry so strongly that matter and light are forced onto very different paths. So an object can be powerful not only because it shines, but because it governs motion. Because it decides what nearby matter is allowed to do. Which paths remain open? Which paths are cut off? Then there is another category altogether. Magnetism. In some parts of the universe, magnetic fields become so extreme that they deserve to be judged almost on their own terms. A magnetar is the perfect example. It is not the largest object, not the brightest long-term engine, not the most massive thing we know. But its magnetic field is so intense that it creates a kind of extremity unlike almost anything else in nature. If power means the ability to impose electromagnetic force on matter with overwhelming intensity, then a magnetar suddenly becomes one of the strongest contenders in the entire universe. And then, of course, there is destruction. This is the category people notice most quickly, because it feels dramatic immediately. Which object can do the most damage? Which event can release the most violence in the shortest time? A supernova can tear a star apart and hurl heavy elements into space. A gamma-ray burst can send an extraordinarily concentrated beam of energy across enormous distances. If we judge the contest only by brief violence, then these events would be impossible to ignore. But even here, we have to be careful. Something can be overwhelmingly destructive for a few seconds, and still not be the most powerful sustained object in the universe. Astrophysics is not only asking what can explode the hardest, it is also asking what can endure. What can continue acting like an engine over immense spans of time? What can keep shaping the environment around it for thousands, millions, or even longer? What can control gas, heat it, expel it, suppress star formation, or even begin to reshape the life of an entire galaxy? We cannot use the word powerful in only one simple way. In astrophysics, power can mean several different things, depending on what you care about most. It can mean energy released each second. It can mean brightness. It can mean gravitational control. It can mean magnetic intensity. It can mean destructive force. Or it can mean long-term influence over the fate of surrounding matter. And once you see that clearly, you also see why the answer may change depending on which standard you choose. When we say most powerful, we might be talking about brightness, or the rate at which energy is released, or gravitational control, or magnetic intensity, or sheer destructive force. And sometimes we may mean something even broader than all of those, the ability of an object to shape what happens around it over a very long time. That change in perspective matters. There was a time when a bright object in the sky seemed important simply because it was bright. But modern astrophysics taught us to be more careful. Brightness can come from many different causes. It can reflect distance, temperature, size, or the violent process of accretion. A dim object may be small and nearby, or enormous and unimaginably far away. A dark object may barely be seen at all and still dominate everything around it through gravity. So again, appearances are not enough. We need sharper categories if we want the question to mean anything. The universe stops feeling like a simple competition between the biggest and the most dramatic things. Instead, different objects begin to stand out for different reasons. One dominates through magnetism, another through explosive violence, another through gravity, another through brightness, another through its long-term influence on everything nearby. The question becomes much more interesting once it is framed that way. So as we move forward, we are not just asking which object sounds the most terrifying. We are asking which objects deserve to lead in each category. And then, which one still stands tallest when those categories are viewed together. Because once power can mean several different things, the universe gives us more than one serious contender. And that means the real comparison can finally begin. Not with one object, but with many. Because the cosmos does not offer a single obvious champion waiting at the front of the line. It offers a whole family of extremes. Some dominate through brightness, some through collapse, some through magnetism, some through gravity, some through a violence so brief that it is almost gone as soon as it appears. So before we settle on any likely winner, we need to let those contenders come forward, one by one. And the first one is the most familiar of all. The ordinary star. A star may not sound like the most exotic answer, but it deserves real respect. At its heart, a star is a balance held together against enormous pressure. Gravity is always trying to pull everything inward. The hot core pushes back outward through nuclear fusion, where light atomic nuclei combine into heavier ones and release energy. That energy streams outward as heat and light, and for long stretches of time, it prevents the star from collapsing under its own weight. And what comes from that balance is extraordinary. A star can shine for millions of years, sometimes billions. In some cases, much longer still. It can light worlds, warm surfaces, drive chemistry, and provide the steady flow of energy from which planets, atmospheres, and perhaps even life can emerge. In that sense, a star is unquestionably powerful. But it expresses that power in a very particular way. Not as a sudden outburst, not as a brief catastrophe. Its strength is steadier than that. More patient, more continuous. a star is less like a blast, and more like a furnace that keeps burning across immense stretches of time. That is what makes stars so important. They are fundamental to the story of the universe. But they may not be the final answer to our question. The next contender enters in a very different way. Not through patience, not through balance, but through collapse. The supernova. A supernova is what happens when the stability of a star fails in the most dramatic way. In one case, a massive star runs low on the nuclear fuel that had been holding gravity back, and its core begins to collapse. In another, a dense, stellar remnant pulls matter from a nearby companion until it crosses a fatal limit. Either way, the star is no longer a steady source of light. It becomes an explosion. For a short time, a supernova can shine with a brightness that rivals an entire galaxy. Matter is thrown outward at enormous speed. Heavy elements are created or scattered into space. The surrounding region is shocked, heated, and changed chemically. So, if we judge power by destructive force, a supernova becomes a very serious contender. It ends the life of a star, reshapes the space around it, and leaves behind ingredients that later worlds may one day be built from. But this is where an important distinction appears. A supernova is immensely powerful, but only for a brief time. Its violence is real. Its consequences are enormous. But it is not something that keeps running for ages. It is not a long-lived engine. It is an event. And after that event fades, what remains can be even stranger. A neutron star. A neutron star is one of the most extreme forms of matter we know. Imagine taking more mass than our Sun and compressing it into a sphere only about the size of a city. Gravity squeezes matter so brutally that electrons and protons are forced together into neutrons. What remains is an object of astonishing density. A place where matter no longer behaves like the familiar material of rocks, oceans, air, or ordinary atoms. A neutron star is not usually the brightest object in the sky. It is not the largest either. But its compactness gives it a kind of authority that is hard to overstate. Gravity near its surface is extreme. Its rotation can be incredibly rapid. And inside it, physics is pushed into conditions we still do not fully understand. It matters in this contest because it shows us matter compressed almost to the edge of what nature seems willing to allow before collapse continues into a black hole. Now let that neutron star spin. Let its magnetic axis lean away from its rotational axis. Let beams of radiation sweep across space as it turns. And now we see it in another form. A pulsar. A pulsar is not a completely different object in the deepest sense. It is a neutron star seen in a special state. What makes it so remarkable is not just that it exists, but how precise it can be. Pulsars rotate with extraordinary regularity. Some spin many times in a single second. Their pulses arrive with such consistency that, when they were first discovered, they briefly seemed almost too orderly to be natural. So, if power means precision, rotational energy, or the ability to accelerate particles and send beams of radiation across space, then pulsars deserve real attention. But even then, they still do not fully settle our question. They are intense. They are exotic. But they still do not quite feel like the final answer. And from here, the story moves toward one of the most extreme objects of all: the magnetar. A magnetar is, in simple terms, a neutron star pushed into an even more extreme magnetic state. Its magnetic field is so intense that our usual comparisons begin to lose their usefulness. This is no longer magnetism in the ordinary sense, or even just a curious astrophysical detail. It is a field so strong that it can dominate how matter behaves around the star. It may not be the brightest, long-lived object. It may not shape an entire galaxy the way some larger systems can. But when it comes to magnetic intensity, it is one of the most extraordinary objects in the universe. By this point, we have already seen that cosmic power can appear in very different forms. A star is powerful in a steady, enduring way. A supernova is powerful in a violent and brief way. A neutron star is powerful through compression and density. A pulsar adds precision, rotation, and focused emission. And a magnetar may be the strongest candidate yet in the realm of magnetism. Now the story turns toward gravity in its darkest form. The stellar black hole. A stellar black hole forms when a very massive star collapses so completely that nothing we know can stop the inward fall. What remains is not a solid object in the everyday sense, but a region of spacetime marked by an absolute boundary. Cross the event horizon, and there is no meaningful path back outward. A black hole is powerful because of what its gravity can do. It controls trajectories. It traps matter and light once they pass too far inward. And yet, a stellar black hole on its own can still be almost invisible. Its power becomes easier to see when matter begins falling toward it. Gas spirals inward. It compresses. It heats. It begins to radiate. And already, we start to see an important pattern. Some of the darkest objects in the universe can become brilliant engines when they are fed. And from there, we move to a much larger scale. The supermassive black hole. These are not black holes, a few times the mass of our Sunday. These are giants containing millions, and sometimes billions, of solar masses, usually found at the centers of galaxies. Their importance is not only that they are bigger, it is that their scale allows them to play a very different role in the universe. A stellar black hole can dominate its local surroundings. A supermassive black hole can shape the inner life of an entire galaxy. But even that is not quite the full story yet. Because a supermassive black hole can remain quiet for very long periods, it can sit in darkness, gravitationally important, but not especially bright. To understand why astronomers care so deeply about them when the subject is cosmic power, we need to take one more step. When a supermassive black hole is actively feeding, the region around it becomes what astronomers call an active galactic nucleus, and in the brightest cases, a quasar. This is one of the most dramatic transformations in astronomy. The black hole itself remains dark, but the matter spiraling toward it becomes so hot, so dense, and so efficient at radiating energy that the central region can outshine all the stars in the galaxy around it. At that point, it stops feeling like just another exotic object. It starts to feel more like an engine. Not something that is extreme in only one direction, but something that begins to matter in several ways at once. It pours out energy, second after second. It holds an extraordinary grip on its surroundings. In some cases, it sends out narrow jets or pushes material outward in powerful winds. And over time, that energy can warm or even clear away the gas that would otherwise collapse into new stars. So it doesn't just shine. Given the right conditions, it can quietly steer what happens next, even on the scale of an entire galaxy. And even here, we should slow down for a moment, because there is still one more contender that deserves a place in the discussion. In at least one category, it may outmatch almost everything else: the gamma-ray burst. A gamma-ray burst is not usually a long-lived object the way a star or a black hole can be. It is a brief event, often linked to catastrophic stellar collapse or the merger of compact remnants. But for that short span of time, it can become one of the most violent outbursts in the known universe. So, if the question is which phenomenon produces the fiercest brief blast, gamma-ray bursts are extremely hard to beat. But we still have to keep an important distinction in place. A gamma-ray burst is powerful in a sudden, explosive way. A quasar is powerful in a sustained, long-lived way. One is a moment of extraordinary violence. The other is an engine that can keep shaping its surroundings over immense stretches of time. And by now, the categories are starting to separate more clearly. The magnetar may be the strongest candidate for magnetic extremity. The gamma-ray burst may be the strongest candidate for brief violence. A supernova is a catastrophic stellar ending. A star is a steady nuclear source of energy. A black hole represents extreme gravitational control. But the feeding supermassive black hole, especially in its quasar phase, begins to look different from all the others. Not simply an extreme field, not simply an explosion, but a sustained engine operating on galactic scales. And once that contrast becomes clear, a deeper question naturally follows. If magnetars dominate in magnetism, and gamma-ray bursts dominate in brief explosive violence, why do astronomers return again and again to quasars and ancient black holes when they talk about cosmic power? Part of the reason is that black holes are also among the most misunderstood objects in all of astronomy. The phrase has become so familiar in popular culture that it almost feels too familiar. It appears in headlines, films, jokes, and metaphors. It has become a catch-all image for anything dark, consuming, or impossible to escape. And that is exactly why we need to slow down here. Because the popular picture is often incomplete and sometimes simply wrong. A black hole is not a cosmic vacuum cleaner wandering through space and swallowing everything around it, is less than Hasson. 5 hash is greater than It is not a hole in the everyday sense, as though something had been torn out of the universe. And it is not powerful because some mysterious light is shining up from inside a glowing abyss. So the first thing to recognize is that not all black holes belong to the same category. Some are stellar mass black holes. These form when very massive stars reach the end of their lives and collapse so completely that nothing known can stop the inward fall. They may contain a few times the mass of the Sun, sometimes more, but they still belong to the scale of stellar death. Then there are supermassive black holes. These are not just slightly larger versions of the same idea. They belong to a very different scale of cosmic structure. Instead of a few solar masses, they can contain millions or even billions of solar masses. And most importantly, they are found very often at the centers of galaxies. That matters enormously. A stellar black hole is the remnant of a star. A supermassive black hole can become something much more central to the structure around it. It often sits in the crowded inner region of a galaxy, where stars, gas, dust, and orbital motion all become especially dense and active. In that setting, it is not just another object among many. It can become one of the defining influences in the galaxy's inner life. If a black hole is dark, then how do we know it is there at all? The answer does not begin with light coming from the black hole itself. It begins with the things around it. Stars move in orbits. Gas swirls. Matter speeds up. And by studying those motions, astronomers can work out that an enormous amount of mass must be packed into an extraordinarily small region. So a black hole reveals itself not by glowing, but by the influence it has on everything nearby. To understand that influence properly, we need to introduce one of the central ideas in black hole physics: the event horizon. This is not a solid surface, like the surface of a planet or a star. It is better thought of as a boundary in spacetime. Outside that boundary, light can still, in principle, find a path outward. Inside it, every future path leads inward instead. That is the deeper meaning of a black hole. It is not only that gravity is strong. It is that space-time is curved so severely that escape is no longer part of the future. Mass bends space-time. And if enough mass is compressed into a small enough region, that bending becomes so extreme that an event horizon forms. Once matter or light passes across that boundary, the geometry itself prevents any return. So a black hole is not an empty hole in the ordinary sense. It is not some cosmic mouth blindly swallowing the universe. It is a region where mass has curved space-time so intensely that beyond a certain boundary, escape is no longer possible. And the difference between a stellar mass black hole and a supermassive black hole is not just a matter of numbers. It is also a difference in role. One is born from the death of a star. The other can become a central presence in the life of a galaxy. And this is where things become a little counterintuitive. Because black holes are often imagined in a very simple way. Dark, silent, almost invisible. So it is worth pausing here for a moment. If the black hole itself does not shine, then where does all that brightness come from? Why do some of these systems end up among the most luminous things we can see across the universe? And more importantly, why do astronomers so often describe them not just as objects, but as engines? The answer is not that the black hole is glowing from inside. The answer lies in what happens around it. Matter usually does not fall straight inward the way rain falls into a drain. Real matter in space almost always has sideways motion as well. It is already orbiting, already moving through the larger structure of the galaxy. So instead of plunging directly inward, it tends to spiral. And as it spirals, it forms what we call an accretion disk. That disk is one of the most important structures in high-energy astrophysics. The gas inside it is moving at enormous speed. Different parts of the disk move differently. The inner regions orbit faster than the outer ones. That difference creates turbulence, magnetic tangling, friction-like effects, and heating. The gas rubs, stirs, compresses, and loses orbital energy. And as it loses that support, it slowly slips inward into deeper and deeper parts of the gravitational well. As gas falls deeper into a black hole's gravitational well, gravitational energy is turned into heat and radiation. That is where the brightness truly comes from. Not from some mysterious light inside the black hole itself. Not from the black hole glowing from within. The light comes from matter that is still outside the event horizon, still visible, and heating up violently as it falls inward. Imagine lifting a heavy stone up a hill. While it is held high, it stores gravitational energy. When it falls, that stored energy is released as motion, impact, sound, and heat. A black hole system follows the same basic logic, only in a far more extreme form. Matter farther out in the gravitational field has one level of energy. Matter closer in has another. As it moves inward, that difference is released, is less than Hasson, 5 is greater than, and the accretion disk is where much of that energy is turned into heat and light. So it helps to picture a black hole in a different way. Not as a mouth, not as some cosmic vacuum cleaner, but as a gravitational depth so extreme that falling matter grows hotter and brighter on the way down. The black hole itself remains dark. The brilliance comes from the material around it. And that explains one of the most striking features of black hole astronomy. The black hole itself is the darkest part of the system. But the environment around it can become one of the brightest sustained sources in the universe. That is why the language can sound contradictory if we are not careful. The darkness is real. The brightness is real too. They just come from different places. Alongside the accretion disk, astronomers sometimes observe jets, narrow, energetic outflows launched along the rotational poles of the system. These jets can travel enormous distances and carry energy far beyond the central region. The detailed physics behind them involves magnetic fields, rotation, and relativistic plasma behavior. But the larger point is simpler. A feeding black hole system does not only pull matter inward, it can also send energy back out into space. Near a black hole, motion becomes extreme enough that ordinary, everyday intuition starts to fail. Gas in the inner disk can move at a substantial fraction of the speed of light. Light coming from those inner regions is shaped by Doppler shifts, gravitational redshift, and the deep curvature of spacetime itself. So the brightest part of the system is not just a source of light. It is also a relativistic environment where space, time, and motion behave in ways far beyond ordinary experience. So the black hole does not become powerful because something escapes from inside the event horizon. The power comes from matter outside the horizon, spiraling inward, heating up, and turning gravitational energy into radiation. In some cases, jets then carry part of that energy outward across immense distances. The black hole is the central gravitational trap. The surrounding region is the visible engine. And now, we can see why the word quiet matters so much. A black hole by itself can indeed be quiet. If very little matter falls toward it, it may remain almost completely dark, detectable mainly through its gravitational effects. Even then, it is still an extraordinary object. It represents collapse, taken beyond every familiar boundary. But a feeding black hole is something very different. Once large amounts of matter begin pouring inward, the darkness at the center becomes surrounded by a system of heat, light, radiation, and violent motion, is less than Hasson. 5# is greater than. At that point, the black hole is no longer just a hidden mass sitting in a galaxy's core. It becomes an active engine. And when that feeding grows especially intense, when the central region becomes so luminous that it can rival or even outshine the rest of the host galaxy, astronomers give that phase a more specific name: a quasar. A quasar is not something separate from a black hole. It is not a different kind of cosmic creature. A quasar is what we see when a supermassive black hole enters an especially active feeding phase, pulling in matter so intensely that the region around it becomes one of the brightest sustained sources in the universe. We are not talking about a heavy object sitting quietly in darkness. We are talking about a system that, under the right conditions, can shape the life of an entire galaxy. The broader class to which a quasar belongs is called an active galactic nucleus. The phrase may sound technical, but the idea itself is fairly simple. The galactic nucleus is just the central region of a galaxy. If that region is quiet, then the black hole there may still be massive and important, but it is not doing very much that would reveal itself across enormous distances. If, on the other hand, large amounts of gas and dust are falling inward, then the nucleus becomes active. It starts radiating intensely. It starts behaving less like a hidden anchor and more like an engine. A quasar is the most luminous end of that story. It is an active galactic nucleus, taken to an extreme, where the feeding becomes so intense that the central region can outshine all the stars in the host galaxy put together. The first time you hear that, it almost sounds unreasonable. A galaxy contains billions of stars. How can one compact central region rival all of that combined starlight? The answer lies in how efficient accretion can be. When matter falls toward an ordinary star, some gravitational energy is released, yes, but the process is limited by the physical structure of the star itself. In a black hole system, matter can fall much deeper into the gravitational well before it disappears from view. As it spirals inward through the accretion disk, it loses orbital energy. That energy does not simply vanish. It is transformed into heat, into light, into radiation across many wavelengths. And that is the crucial point. In this situation, gravity becomes more than a force that pulls. It becomes part of the energy source. Matter falls inward. Speeds rise. Turbulence, compression, magnetic effects, and friction-like processes heat the gas. The closer the gas moves toward the center, the hotter and brighter the disk becomes, is less than Hasson. 5' is greater than. By the time matter reaches the innermost visible regions outside the event horizon, the system has become extraordinarily intense. That is why quasars matter so much. They show us that a black hole is not simply a destination where matter disappears. Under the right conditions, it becomes part of one of the most efficient engines nature can build. A quasar is not a separate object from a black hole. It is a phase in which a supermassive black hole is feeding so strongly that the surrounding accretion flow becomes overwhelmingly bright. That brightness comes from matter outside the event horizon, not from the black hole itself glowing from within. And that is exactly why the quasar becomes one of the strongest candidates in our search for the most powerful object in the universe. Now we can sharpen the question further. Why can the brightest quasars outshine the galaxies that host them? Because stars, for all their beauty, release their energy in a slower and more distributed way. A galaxy shines through the combined fusion light of vast numbers of stars, each acting as a long-lived source of energy. A quasar does something different. It concentrates enormous energy release into a comparatively small region, and it does so with extraordinary intensity. That is why a single galactic center, under the right conditions, can compete with the light of billions of stars spread across the whole galaxy. The galaxy is wide and spread out across enormous distances. The quasar is different. Its power is concentrated into a very small central region, and its brightness can become so intense that, from far enough away, that central source can dominate what we see. But even that is still not the whole story. If quasars were only bright, they would already be extraordinary. But the deeper reason they matter is that they do more than radiate. They affect what happens around them. They push on their surroundings. They change the behavior of gas. They influence what a galaxy can become. One way they do this is through jets. In many active systems, energy and matter are launched outward along the rotational poles in narrow beams that can travel far beyond the central region. These jets are not just visual details. They are ways for the black hole system to send energy back into the galaxy and beyond it. They can heat surrounding gas. They can disturb matter that might otherwise settle and cool. And in some cases, they can influence whether gas collapses to form stars or remains too hot and spread out to do so. Another part of the story comes from radiation itself. Light does not just illuminate. Radiation also carries momentum, is less than Hasson. 5 is greater than. So when a quasar shines with enormous intensity, that radiation can push against the very gas that is falling inward. It can slow further accretion. It can help drive winds outward. It can help clear material from the inner parts of the galaxy. A quasar is not just sitting at the center of a galaxy and passively existing there. It is acting on the galaxy around it. It changes how much cold gas remains available. It influences where future stars may form and where they may not. In that sense, it becomes part of the galaxy's history, not just part of its structure. We are no longer talking about a heavy object hidden in the dark. We are talking about a system that can influence the future of an entire galaxy. That picture is very different from the familiar, popular cliché about black holes. The cliché says they simply swallow things. The real picture is much richer. A quasar can be seen across immense distances. It can reveal itself from the deep past of the universe. It can affect its host galaxy through heating, winds, and jets. And for a period of time, it can become one of the dominant engines in that entire galactic system. It combines several kinds of power at once. It carries the gravitational authority of a supermassive black hole. It releases extraordinary energy through accretion. It can outshine the galaxy that hosts it. And through jets, winds, and radiation pressure, it can shape the future of matter on galactic scales. This is no longer just a bright source in the sky. It is a long-lived cosmic engine. And when the quasar finally comes into focus like this, something shifts. The question we started with no longer feels distant or abstract. We are no longer comparing isolated extremes. Not just the strongest magnetic field, not just the most violent flash, not just the heaviest dark object. Instead, we begin to see a different kind of contender taking shape. One that does not win in only a single category, but quietly gathers several of them together. And in that light, the answer starts to settle. The feeding supermassive black hole, in its quasar phase, begins to look less like one possibility among many, and more like the strongest answer to the question we have been following all along. The most powerful sustained object in the universe. And just when the answer begins to feel clearer, another problem appears. Because if this really is the best answer, then we are pushed toward a much more uncomfortable question. How did an engine like this appear so early? It is less than Hasson. 5 is greater than. How did a young universe, which should still have been small, rough, and unfinished, already produce central engines of such intensity. How did a cosmos, still in its youth, create objects that seem not newly forming, but already strikingly mature? So the quasar is not only powerful, it may also be early in a way that is difficult to explain. And if that is true, then the mystery changes. We are no longer asking only what the most powerful object in the universe is. We are also asking why the universe seems to have built it so soon. We have been more careful about what power really means. We have compared the major contenders. And step by step, the feeding supermassive black hole, especially in its quasar phase, has begun to look like the strongest answer. But now, a deeper issue comes into view. The problem is not that these objects are too dramatic. The problem is that they may be appearing too early. And that difference matters a great deal. Science is not troubled simply because something is grand or extreme. Science becomes troubled when the timing stops making sense. An astonishing object is not a problem if the universe had enough time to build it. But when something massive, luminous, and already mature seems to appear before the timetable comfortably allows it, then the question changes completely. We are no longer just admiring an extraordinary discovery. We are being forced to re-examine the sequence of events that were supposed to produce it. So now we need to slow down and rebuild the standard picture, the one cosmologists expected before these tensions became so sharp. In the usual story of cosmic structure formation, the early universe does not begin with galaxies already assembled. It begins with tiny irregularities. After its earliest hot phases, the young universe is remarkably smooth on large scales, but not perfectly smooth. From one region to another, there are slight differences in density. And those small differences are the seeds from which later structure grows. Then gravity begins its slow work. Regions that are a little denser than average pull in more matter. As they gather more matter, they become denser still, and their gravity grows stronger. Over time, gas and dark matter collect into halos and filaments. The larger cosmic web begins to take shape. But this is not a sudden jump from simplicity to grandeur. It is a gradual process, where small beginnings are slowly amplified over time. That slow growth is a crucial part of the story. Because in the standard picture, the first structures are expected to be small. The first stars should appear in relatively simple environments is less than Hasson. 5# is greater than 2 the first. Galaxies should still be young, irregular, chemically primitive, and far from the large, organized systems we see later in cosmic history. In that same picture, black holes should also begin in a modest way. Perhaps as the remnants of massive early stars. Perhaps as small seeds that then grow through accretion and mergers over very long spans of time. And that last part is where the real difficulty begins. Over long spans of time. Because the standard story unfolds step by step. First, the first stars. Then primitive galaxies. Then mergers, growth, and larger systems. then black holes becoming more massive as they feed and combine. In other words, complexity is expected to arrive gradually. Enormous galactic centers are not supposed to appear right away. They are supposed to emerge only after enough time has passed. And why does that story need time? Because every stage comes with its own limit. Gas has to cool. Matter has to gather. Stars have to form. Heavy elements have to be produced. Gravitational wells have to grow deeper. Smaller systems have to merge into larger ones. And if black holes begin as small seeds, then they also have to grow, and that growth is not infinitely fast. In this picture, the universe does not rush straight to finished structures. It builds them over time. So the standard cosmological story is not saying that large structures can never appear. Of course they can. It is saying that they should appear gradually. Tiny irregularities first, then the first stars, then primitive galaxies, then larger systems through mergers and continued growth, and black holes growing in stages along the way. The key word here is not impossibility. It is timescale. The James Webb Space Telescope did not simply give us sharper images of the same old story. It gave us a much clearer view of the early universe itself. It allowed astronomers to look back to a time when the cosmos was still very young, only a few 100 million years after the Big Bang. And in several cases, what it revealed seemed more mature than many researchers expected. Massive galaxies appearing very early. Structured systems appearing very early. Active black holes appearing very early. Perhaps even galactic centers that already look surprisingly developed only a short time after the beginning. That is where the tension comes from. Not because galaxies exist. Of course they do. Not because black holes exist. Of course they do. Is less than ℏ. 5# is greater than. The tension is that some of these objects seem to have moved through several stages of growth before the cosmic clock seems comfortably ready to allow it. Imagine being told that a great city has only just begun building its first skyscraper. You arrive expecting trenches in the ground, exposed steel, workers pouring the first levels, concrete still drying in its frames. But instead, the tower is already finished. Windows are shining. Elevators are running. Lights are already on near the top. The problem is not that skyscrapers can exist. The problem is that this one seems to have appeared before there was enough time to build it. And that is the right way to think about the tension here. It is easy to react to surprising observations with language that is too dramatic, and to say something loose like, "This should be impossible." But that is not really the most careful way to describe the situation. The more accurate point is subtler than that. These objects may not be impossible in principle. The question is whether the universe had enough time to produce them through the ordinary path we thought it would follow. Were the first stars more massive than we usually assume? Were the earliest black hole seeds larger than the standard picture often suggests? Did gas fall inward faster than expected? Were mergers more efficient? Did the first dark matter halos form earlier and deepen more quickly? Or are some of our first interpretations still too aggressive, so that the tension may soften as the data improves? All of those possibilities are still very much alive. And that is exactly what makes this such an interesting scientific moment. We are not watching cosmology fall apart. We are watching it get tested where it is hardest to test, at the beginning, where small differences in the early conditions can lead to enormous differences later on. Webb changed the conversation because it gave us a much clearer view of the young universe. And in that young universe, astronomers have found signs of galaxies that seem too massive too early, systems that seem too structured too early, and black hole activity that may also have begun too early. The issue is not that such objects could never exist. The issue is that the usual route for building them seems to need more time than the early universe may have had available. And now the tension becomes especially sharp when we focus on black holes. Because black holes do not just need matter around them. They also need a growth history. If a supermassive black hole is already present and actively feeding in the young universe, then something unusual must have happened, is less than Hasson. 5 hash is greater than either it began from a seed that was already unusually large, or it grew at an extraordinary rate, or both. In any case, the slower and more comfortable version of the story becomes harder to keep. And this matters because the quasar, which now looks like one of the strongest answers to our title, depends completely on that history. A quasar is not just a black hole sitting there. It is a black hole that has become an engine. To reach that state, it must already be massive enough, centrally placed enough, supplied with enough fuel, and active enough to reshape what happens around it. That is a remarkable amount to ask from a universe only a few 100 million years old. So, the question has now changed in an important way. We are no longer asking only which object deserves the title of the most powerful in the universe. We are also asking whether the universe built that object earlier than expected. Whether one of the greatest engines in nature may have switched on before the larger structure around it should have been ready. And that is why these observations feel so striking. They do not suggest only early light. They suggest, in some cases, early maturity. Not just the first hints of structure, but systems that already seem to have moved through much of the slow process we thought should take longer. They hint that the universe may have organized itself faster, or at least differently, than our cleanest stories once suggested. Up to this point, the mystery has mostly felt visual. Ancient galaxies seem more mature than expected. Central engines seem brighter than expected. Supermassive black holes seem to have appeared earlier than expected. But now the story becomes more demanding. Because from here on, the question is not just what looks surprising. It is what the physics can actually allow. And in its simplest form, that physics is not especially generous. In the most straightforward picture, a black hole grows through accretion. Matter falls toward it, gas spirals inward. Some of that matter crosses the event horizon and adds to the black hole's mass. Said quickly, that sounds simple. But the real difficulty appears when we slow down and ask what happens to the gas before it gets there. Gas does not usually fall neatly and quietly into a black hole. Real gas in a galaxy already has motion. It is orbiting, colliding, stirring, tangling with magnetic fields, and responding to the deeper gravitational pull as it moves inward. So instead of dropping straight in, it forms an accretion disk. The inner parts of that disk move faster than the outer parts. Different layers rub past one another. Motion is turned into heat, is less than ℏ. 5 is greater than, the gas grows hot, then hotter, and in the inner regions, extremely hot. And hot gas radiates. That simple fact is where the bottleneck begins. Because the same process that allows a black hole to grow also makes the system shine. As the accretion flow becomes brighter, more light and high-energy radiation stream outward from the disk. And that radiation is not just something we observe from a distance. It also acts back on the inflowing gas. You can picture it this way. Gas is trying to fall inward under gravity. At the same time, intense radiation from the bright accretion disk is pushing outward. Light carries momentum. So when radiation strikes matter, it can push on it. That means the gas falling inward is caught between two competing effects, gravity pulling it in and radiation pushing it back out. This is the basic logic behind the Eddington limit. We can build that logic slowly. Gravity pulls the gas inward. As gas falls in, it heats up and the system becomes more luminous. As the luminosity rises, the outward push from radiation becomes stronger. So the more efficiently the black hole feeds, the more strongly the system begins to resist additional inflow. If the luminosity stays modest, gravity remains comfortably in control, and the gas continues inward. But if the luminosity becomes high enough, radiation pressure starts to seriously oppose the inflow. And there is a threshold where the two effects come close enough into balance that simple, steady growth becomes difficult to maintain. That threshold is what astronomers call the Eddington limit. And the important thing here is not the equation by itself. The important thing is the physical idea inside it. The Eddington limit is not some arbitrary rule that theorists invented. It comes from a real competition between gravity and radiation. Feed the black hole harder, and the system shines more brightly. A brighter system pushes outward more strongly. And that stronger outward push makes it harder for even more gas to keep falling in. In that sense, the brilliance of the engine begins to interfere with its own fuel supply. That is what makes this part of the physics so fascinating. And also so restrictive. A black hole can grow by pulling matter inward. But the more effectively it feeds, the more brightly the surrounding gas begins to shine. And that radiation does not just announce the growth. It also begins to oppose it. A black hole grows through accretion. Gas falls inward, heats up, and radiates. That radiation carries momentum outward and pushes on the same material that is trying to fall in, is less than her own. 5# is greater than. The Eddington limit is the approximate point where that outward radiative push becomes strong enough to seriously oppose further steady inflow. So black hole growth is not as simple as endlessly pouring fuel into a deep gravitational well. The system brightens as it feeds, and that brightness starts to work against the feeding itself. And that leads to the next consequence, which is where the timing problem becomes much more precise. If a black hole is growing near the Eddington limit, then it can certainly become larger, but not all at once. Its growth follows a time scale. It builds through repeated increases over time. Not instantly. Not effortlessly. That means the growth history matters enormously. If you begin with only a small seed black hole, then even under optimistic conditions, it still takes a long time to turn that seed into a supermassive object. And when we say a long time, we mean time that has to be accumulated carefully, because each stage of growth has to survive the self-regulating effect we have just described. The black hole cannot simply feed without consequence. The more efficiently it feeds, the more strongly the radiation begins to push back. Now imagine that the first black hole seeds were just the remnants of massive early stars. Then the starting point is not a giant black hole at all, but something much smaller. To grow from that modest beginning into the kind of supermassive black holes inferred in the young universe, you need repeated growth over long intervals, with relatively few interruptions, and often at rates close to the highest steady pace the physics comfortably allows. And even that assumption is already quite demanding. Why? Because real astrophysical environments are not tidy. Fuel supplies change. Gas can be heated and pushed away. Star formation can consume material that might otherwise have fed the black hole. Feedback from the growing black hole can disturb the inflow. Galaxy mergers may help in some ways, but they also make the environment more chaotic. So the idea that a black hole could sit there and feed almost continuously, near its radiative limit, for a very long time, is not really the conservative assumption. It is already a very generous one. And that is exactly why the earliest quasars and the earliest supermassive black hole candidates attract so much attention. Even if we allow them near continuous, near maximal growth, some of them still remain difficult to explain if they began from seeds that were too small. The problem is not subtle. In the first few 100 million years after the Big Bang, time itself is limited. And that limited time becomes one of the hardest constraints in the entire story. The mathematics, in the end, creates a very specific problem. It does not tell us that black holes can never become large. Of course they can. What it tells us is narrower, and in some ways more troubling than that. If you begin with ordinary seed masses, And if growth is limited by the usual balance between gravity and radiation, then reaching enormous size takes longer than the early universe seems comfortably able to provide. That is the bottleneck. Not impossibility. Not some dramatic violation of physics. Simply not enough time if we stay with the most ordinary assumptions. The Eddington limit gives us a kind of self-regulating ceiling. The brighter the accretion flow becomes, the stronger the outward radiative push becomes as well. And growth near that ceiling is already a fairly optimistic picture because it assumes a long, efficient, and relatively uninterrupted supply of fuel. But even that optimistic picture can struggle to explain some of the earliest massive black holes if they began from small seeds. That is why this timeline problem is not just a dramatic reaction to surprising images. It comes from the arithmetic of growth under real physical limits. When people hear that black holes are greedy, it is easy to imagine that greed means unlimited speed. But in astrophysics, that is not how it works. A black hole may be able to accept matter, yes, but the surrounding environment decides how efficiently that matter can actually arrive. The accretion disk has to move angular momentum outward. The gas has to cool and continue flowing inward. The radiation must not push too much of the fuel away. So growth is not controlled by appetite alone. It depends on transport, regulation, and feedback. We are not just looking at an object that happens to be very large. We are looking at an object whose existence seems to require a demanding growth history, compressed into a very short stretch of cosmic time. A galaxy-scale engine, appearing this early, is not just bright or impressive. It suggests that several difficult steps may have happened quickly, efficiently, and perhaps more than once. If ordinary accretion from ordinary seeds is too slow, then we are naturally pushed toward less ordinary possibilities. Maybe the first seeds were already much larger than the remnants of normal stellar collapse would suggest. Maybe accretion in the early universe was not steady in the usual way. Maybe it rose above the simple limit for meaningful stretches of time. Maybe the geometry of the inflow was different. Or maybe the whole growth environment in the early universe was denser, messier, and more efficient than the simplest version of the story assumes. We have not simply found black holes in the early universe. We have found signs that some of them may already have become enormous, active, and in some cases quasar-like, at a time when the cosmic clock still seems very young. And the bottleneck behind that tension is now clearer too. Ordinary growth from ordinary seeds, limited by the usual balance between gravity and radiation, often appears too slow. Science does not respond to a bottleneck like that by ignoring it. It responds by asking what physical routes nature may actually have used. Not miracles, not convenient storytelling, but real mechanisms that researchers can model, debate, test, and compare. And in broad terms, three major possibilities begin to stand out. The seeds may have started larger. The feeding may have been faster. Or the early universe may have behaved in ways that make the simplest background picture incomplete. So we need to take those possibilities one at a time carefully, because each one may solve part of the puzzle, and none of them solves everything without raising new questions of its own. 1. Direct collapse. Black holes. What if the seeds were born large? Maybe we have been picturing the wrong kind of seed. In the simplest version of the story, black holes begin as the remnants of massive stars. A star lives, burns through its fuel, collapses, and leaves behind a black hole that is still relatively modest in mass. From there, that black hole has to keep growing through accretion and mergers over a very long time. But if the starting seed is too small, the timing becomes much harder to make work. A very small seed has a long way to go. Even under optimistic conditions, growth has to repeat again and again, and the early universe does not offer unlimited time for that process. What if some black holes did not begin small at all? That is the basic idea behind direct collapse black holes. Instead of starting with the remnant of an ordinary star, perhaps under special conditions, an enormous cloud of primordial gas collapsed almost directly into a very massive black hole seed. Not a small seed struggling upward over hundreds of millions of years, but a seed already heavy enough to make the later growth history much easier. The appeal of the idea is fairly obvious. If the problem is that small seeds need too many rounds of growth, then one solution is to begin with a larger seed. A larger starting point means less distance to cover later. But this picture does not come easily. It needs special conditions. A gas cloud does not usually stay together as one giant collapsing body. As it cools, it tends to fragment. And once it fragments, stars begin to form. Is less than Hasson. 5 is greater than. At that point, the cloud is no longer collapsing in one coherent way. It breaks into smaller pieces, and the path toward a giant seed becomes much harder. So the direct collapse idea only works if something prevents that fragmentation from happening too easily. The cloud has to remain hot enough, smooth enough, or stable enough to collapse more coherently. In practice, that means the early universe would need to provide not just dense gas, but the right thermal history, the right chemical conditions, the right radiation environment, and the right dynamical setting as well. And that is exactly why this idea is both attractive and difficult. Its strength is clear. It addresses the seed problem directly. But its weakness is clear too. It may depend on circumstances that were rare. And if those circumstances were too rare, then direct collapse may help explain some early massive black holes. But not all of them. So, the direct collapse picture asks us to consider a different beginning. Maybe some of the earliest black hole seeds were not small stellar leftovers at all. Maybe some were born already massive because huge primordial gas clouds collapsed almost directly into them. That would solve the problem of starting too small. But it leaves us with another question just as important. How often could the early universe actually create the special conditions needed for that kind of collapse? 2. Black hole mergers. What if many small seeds combined rapidly? The second possible route keeps the seeds relatively small, but changes the way growth happens. Instead of one black hole slowly building upward through accretion alone, perhaps many smaller black holes formed early and then merged quickly in dense environments. In some ways, that idea is quite natural. The early universe was already beginning to build structure. Dark matter halos were forming. Primitive galaxies were colliding and merging. And if small black hole seeds were already living inside those young systems, then some of those seeds might eventually have been brought together as the larger structures around them merged. And when black holes merge, growth does not happen as a slow drip. It happens in jumps. Instead of relying only on a continuous flow of gas feeding one object, you allow the broader growth of cosmic structure to help build something larger. Galaxy mergers can bring in fresh material. They can stir the gas. They can channel matter towards central regions. And in some cases, they may bring multiple black holes into the same environment, where they can move inward, form a pair, and eventually merge. At first, this sounds like exactly the kind of shortcut we might need, is less than Hasson. 5# is greater than turns out. But it turns out not to be quite so simple. The difficulty is not in imagining mergers in general. The difficulty is in making them happen early enough, often enough, and efficiently enough. Black holes do not merge the moment their host galaxies pass near one another. A great deal has to happen in between. Orbital energy has to be removed. Dynamical friction has to bring the objects inward. Gas, stars, and the surrounding system all have to help drain energy from the pair before a final merger can take place. So mergers can certainly help. But they are not a magic solution. They are themselves part of a timed process inside a universe where time is already the problem. The same cosmic clock that makes early black holes difficult to explain also limits how quickly merger-driven growth can happen. There is another complication too. Mergers can increase mass in jumps, yes, but the black holes still have to exist in large enough numbers to begin with. So this route does not remove the seed problem completely. It still depends on an early population of seed black holes, and those seeds need to form in environments dense enough and active enough for repeated mergers to become realistic. Even so, the merger pathway remains an important part of the discussion, because it reminds us that black hole growth is not only about feeding. It is also about assembly. A black hole can grow not only by drawing in gas, but by joining with others as galaxies themselves grow through collision and combination. Maybe the early universe produced many smaller black hole seeds, and then brought some of them together rapidly through dense environments and frequent interactions between young galaxies. That could speed up growth in jumps, rather than relying only on slow, continuous accretion. But it still asks a lot from the early universe. Efficient structure formation, efficient orbital shrinking, and enough time for repeated mergers to actually finish. So it may help a great deal, but it does not make the problem disappear cleanly. 3. Super Eddington accretion. What if the feeding was stranger? The third possible route goes more directly at the bottleneck itself. In the last part, we followed the logic of the Eddington limit. The harder a black hole feeds, the brighter the accretion flow becomes. And the brighter it becomes, the more strongly radiation pushes outward against further inflow. That creates an approximate ceiling for steady feeding. But the real universe does not always behave in the cleanest possible way. And that is where the idea of super Eddington accretion enters. This does not mean the Eddington argument was wrong, is less than ℏ. 5 is greater than. It means that real accretion flows may sometimes be more complicated than the simplest version of the picture. Under certain conditions, matter may still flow inward faster than the ordinary steady limit would suggest. Perhaps the gas falls through especially dense channels. Perhaps the radiation escapes more strongly in some directions than in others, instead of pushing equally everywhere. Perhaps the inflow becomes so thick, clumpy, or structured that the system can swallow mass faster than the simplest models would allow. That is an important point. This idea does not throw away the mathematics. It changes the assumptions behind the simplest version of the mathematics. The classic Eddington picture works most cleanly when the geometry is relatively simple and the radiation field behaves in an orderly way. But real black hole environments, especially in the early universe, may have been much messier than that. And if they were, then feeding may sometimes have exceeded the neat, steady limit long enough to matter. If that happened, then even a black hole that began from a modest seed might still have grown much faster than we would otherwise expect. A super Eddington phase would not erase the whole problem, but it could compress the schedule. It could allow significant growth in a much shorter stretch of cosmic time. But this route also comes with real questions. How common were such phases? How long could they last before feedback disrupted the inflow? Could they happen more than once? And could they explain the full range of early black hole masses, or only some of them? So once again, we have a promising possibility, but not a complete answer that solves everything on its own. So the super Eddington idea is fairly simple at its core. Maybe some early black holes fed faster than the ordinary steady limit would suggest. Not because the Eddington argument failed, but because the real conditions of early accretion may have allowed matter to keep flowing inward despite strong radiation. If that happened, then growth could have been accelerated quite a bit. But the main uncertainties remain the same. How often? For how long? And under what kinds of environments? By this point, the three major pathways are starting to come into view more clearly. Larger seeds through direct collapse. Faster build-up through mergers. And more aggressive feeding through super Eddington accretion. But those are not the only ideas in the discussion. Around them are several other possibilities that make the picture more nuanced. One of those possibilities involves population 3 stars. The first generation of stars is less than ℏ. 5 is greater than. If these earlier stars were unusually massive on average, then the black hole seeds they left behind may also have been somewhat larger than the seeds formed later in more metal-rich environments. That does not solve the full problem by itself, but it does move the starting point upward. Another factor is early metal enrichment. In astrophysics, the word metals means elements heavier than hydrogen and helium. Those elements matter because they affect how gas cools, fragments, and forms stars. If the chemical history of the early universe was different in important ways, then the pathways by which gas collapsed may also have been different. Gas might fragment more easily in some environments, or remain in larger, coherent structures in others. Then there is the question of faster halo formation. If dark matter halos assembled earlier, or more efficiently, than some simple expectations suggest, then the gravitational wells needed to gather gas and build early galaxies may also have formed sooner. That would help all the other pathways, because deeper wells would mean denser environments, earlier structure, and earlier opportunities for central black holes to grow. And there is another possibility, a wider one. It may not be only about black holes. It may be about the stage they were born into. Our picture of dark matter in the early universe might still be missing something subtle. If that invisible framework gathered and collapsed a little differently, if structure began to organize itself earlier or more efficiently than our simplest models suggest, then the whole timeline could shift. Galaxies might appear sooner. Their centers might grow faster. And the black holes, at that point, the puzzle quietly expands. It is no longer just about how black holes grow, but about how the universe itself began to build structure. And it is worth pausing here, because this part can be misunderstood, is less than number. These ideas are not patches added afterward to protect a theory. They come from ongoing work, from people trying to follow the evidence wherever it leads. Each possibility carries its own hints, its own uncertainties, its own difficulties when we try to model it carefully. And each one makes predictions about what we should eventually see. That is what gives this moment its importance. Not speculation for its own sake, but a method is less than hasone. When the data becomes difficult, astronomers do not simply reach for convenient answers. They build scenarios, they test assumptions, and they ask a grounded question: is less than number? If this picture is right, what should the universe show us next? So by now, the broad picture is becoming clearer, is less than hasone. 5 hash is greater than. There are 3 main routes people talk about most often. Direct collapse could provide larger initial seeds. Mergers could assemble mass more rapidly by combination. Super Eddington feeding could allow faster than usual accretion under special conditions. And around those main ideas, other factors may also matter. Population 3 stars, the chemical history of the early universe, the timing of halo formation, and the detailed behavior of dark matter itself. This is not hand-waving. It is exactly how science works, when one explanation is not yet enough. Each idea may solve part of the puzzle, but none removes every difficulty without raising new questions. So where does that leave us? In a place that is uncertain, yes, but also very revealing. The early universe may not have relied on just one pathway. Perhaps some black holes were born from direct collapse. Perhaps others grew through repeated mergers in dense young environments. Perhaps some went through short episodes of unusually rapid feeding. Nature often does not choose one perfectly clean mechanism. It may use several at once. And if that is true, then the black hole at the center of this story becomes even more important. It is no longer just a strange object whose mass needs explaining. It becomes a record of the environment that built it. Its existence may carry clues about the temperature of primordial gas, the chemistry of early collapse, the formation of dark matter halos, the merger history of young galaxies, and the feedback physics of accretion itself. By this point, the black hole has already become much more than a dark object in empty space. It is not just a place where escape becomes impossible. It is not just an extreme gravitational object. It is not just the engine behind a quasar. And now the story leads us to a deeper possibility. A supermassive black hole at the center of a galaxy may do more than simply live there. It may help shape what that galaxy becomes. That is a much bigger claim than brightness alone. Brightness can attract attention. But influence over a galaxy's future is something deeper. And if that idea is right, then the role of the black hole becomes remarkably large compared with its size. A compact object at the center, tiny compared with the full scale of a galaxy, may still help determine whether the surrounding system continues to grow, continues to form stars, or gradually grows quiet. To understand that, we need one of the key ideas in modern galaxy evolution: coevolution. The word simply means that a black hole and its host galaxy may not grow separately, each on its own path, is less than has sown, 5 hashes greater than. Instead, they may evolve together, influencing one another through shared matter, shared gravity, and shared feedback over long stretches of time. And the reason astronomers began taking that idea seriously did not come from poetic language. It came from patterns in the data. When researchers studied galaxies and the black holes at their centers, they found that the properties of those black holes often seemed linked to the properties of the galactic bulge around them. In other words, the central black hole and the surrounding stellar structure did not look randomly paired. Their histories appeared connected. That is already an important clue. But a clue becomes more meaningful once we understand the mechanism behind it. And in this case, that mechanism is what astrophysicists call feedback. The word feedback may sound harmless at first. But around a supermassive black hole, it can become one of the defining forces in the life of a galaxy. When matter falls inward and the black hole begins feeding, the energy released does not always stay near the center. Some of it travels outward through radiation, some through winds, some through shocks, and in some systems, through jets. Once that energy reaches the gas inside the host galaxy, it can begin to change what that gas is able to do. And that matters because a galaxy depends, in a very practical sense, on its gas supply. If enough cold gas remains available, it can gather into clouds. Those clouds can fragment into denser regions. And from there, new stars can form. If the gas is heated, stirred, blown outward, or prevented from cooling, then star formation begins to slow. In some cases, it can slow dramatically. The galaxy gradually becomes quieter. So much of galaxy evolution comes down to what happens to the gas. And through feedback, the central black hole may become one of the most important regulators of that gas. The sequence is not mysterious once you lay it out. Matter falls toward the central black hole. The accretion flow grows bright. Radiation moves outward. In some galaxies, winds are launched from the nucleus. In others, jets carry enormous energy far from the center. That injected energy then interacts with the surrounding gas. Gas can be heated. Heated gas does not collapse as easily. Gas can also be pushed outward. And gas that is pushed out or kept hot is no longer available in the same way to form future generations of stars. Over time, the galaxy's star-forming reservoir can shrink or become much harder to use. That is why feedback matters so much. The black hole does not need to swallow an entire galaxy to influence it, is less than Hasson, 5 is greater than. It only needs to interfere with the galaxy's supply of usable gas. Change the state of the gas. Change where it can go. Change whether it can cool. And you begin to change the future of the galaxy itself. So the picture becomes clearer. A galaxy can keep making stars only if enough cold gas remains available. A feeding supermassive black hole releases energy through radiation, winds, and jets. That energy can heat gas, expel gas, or keep gas from cooling efficiently. In that way, the black hole may regulate the galaxy not by consuming all of it, but by changing whether the raw material for future stars can still be used. This leads us to one of the most important words in the discussion: quenching. Astronomers use that word when star formation in a galaxy has been strongly reduced or shut down. Put more simply, the galaxy stops making many new stars. Its bright, young, stellar populations begin to fade with time. The system grows redder, older in appearance, and more dominated by stars that formed earlier. Now, galaxies can be quenched for more than one reason. Their environment matters. Their gas supply matters. Interactions with surrounding structure matter too. But feedback from a central black hole has become one of the strongest candidate explanations for why some massive galaxies stop forming stars efficiently. And by this point, the black hole is starting to look very different from the familiar popular image. It is no longer just a dark object sitting at the center. It is no longer only an extreme gravitational phenomenon. It is beginning to look like something that can shape the long-term evolution of the galaxy around it. This is where people sometimes use dramatic phrases like galaxy killer. That phrase should be handled carefully. A black hole does not usually destroy a galaxy by tearing all of its stars apart. the stars already formed generally remain where they are. The galaxy still exists. But if feedback shuts down future star formation, then the galaxy's future changes. In that sense, the black hole can help turn a vigorously star-forming system into a quieter, more dormant one. At the same time, the black hole may also play a constructive role, though in a much subtler way. Feedback is not only about destruction. By regulating how gas collapses, limiting runaway growth, redistributing matter, and changing the thermal state of the galaxy, a central black hole may help shape the final character of its host. It may help explain why galaxies do not simply turn all of their gas into stars at once. It may help set the balance between a dense central region and the wider structure around it is less than ℏ. 5 is greater than, and in some cases, it may even compress gas in certain regions, while suppressing star formation in others. So the black hole is not only something that shuts processes down. Under the right conditions, it also helps shape how growth unfolds. Sometimes it limits what can happen next. Sometimes it changes the conditions under which the galaxy continues to evolve. That is one reason why the idea of dead galaxies in the early universe is so striking. In informal astronomical language, a dead galaxy is not a galaxy that has disappeared. It is a galaxy in which star formation has already dropped dramatically. And when astronomers find hints of such systems at very early times, the tension becomes much stronger. Why? Because it suggests that two difficult things may have happened in rapid succession. First, the galaxy must have built up a substantial population of stars very early. Then, not long afterward, something must have reduced or shut down further star formation. That is a very compressed timeline. So, an early dead galaxy is not just another curious observation. It creates a timing problem on top of an existing timing problem. The galaxy seems to have grown quickly and then quieted quickly as well. To produce that outcome, the mechanisms regulating the system, possibly including the central black hole, would need to have been working with remarkable efficiency. Gas gathers inside the galaxy. Stars begin to form rapidly. A central black hole grows. The black hole becomes active. Energy is released outward. Gas is heated or pushed away. Star formation weakens or stops. The galaxy moves from a more youthful, active state into a quieter one. And if that whole sequence happens early enough, then the black hole is not just appearing late in an already mature galaxy. It may be helping shape that galaxy from near the beginning. That is why feedback matters on galactic scales. A supermassive black hole can influence gas far beyond its immediate surroundings. It can heat gas, drive gas outward, prevent efficient cooling, and in the end, help quench star formation. So early dead galaxies matter not only because they imply rapid growth, but because they may also imply rapid shutdown. And that makes it more plausible that black holes became powerful enough, early enough, to shape galaxies before those galaxies were fully mature. So the black hole may not just be sitting quietly at the center. It may be doing something more subtle, helping decide whether a galaxy keeps growing, keeps forming stars, or settles into a quieter phase much earlier than we might expect. What we are really seeing is a combination of effects: gravity pulling inward, radiation pushing outward, heat, motion, and gas all interacting over enormous distances. And taken together, they create something that feels almost disproportionate. Because the region doing all of this is surprisingly small. A compact center influencing a system that can stretch across tens, even hundreds of thousands of light years. And that imbalance is part of what makes the story so striking. The biggest thing in view is not always the most influential. A galaxy may look like a vast spread of stars, but under the right conditions, the quiet darkness at its center can help shape what that galaxy becomes. So the meaning of most powerful begins to shift. It is no longer just about brightness, or energy per second, or even the depth of gravity alone. It starts to mean something broader: influence, regulation, the ability of one small region to guide the life cycle of an entire galaxy. So the question in front of us becomes sharper now. If black holes can help quench galaxies, then the most powerful object in the universe may not be defined only by brightness. It may also be defined by influence, by how deeply one object can shape the future of an entire system. A quasar is certainly bright enough to dominate the light of a galaxy, and the supermassive black hole behind it may influence the gas, the stars, and the long-term evolution of its host. By this point, it is easy to feel that we are already close to the answer. But this is also the moment when the story becomes larger than the object itself. Because once something this extreme appears so early, it stops being only an astrophysical curiosity. It starts to test the larger picture that was supposed to explain how such things came to exist at all. So now we need to widen the lens. We are no longer asking only whether we have found the most powerful object in the universe. We are asking whether objects like this, especially so early in time, simply add another remarkable chapter to astrophysics, or whether they place real pressure on the broader cosmological story that is meant to produce them. That broader story has a name. It is the standard cosmological model, often called lambda cold dark matter, or lambda CDM. In simple terms, it gives us a broad account of how the universe grew. The universe began hot and dense. It expanded and cooled. Tiny irregularities were present very early on. Dark matter provided the gravitational framework within which later structures could grow. Ordinary matter fell into that framework. Galaxies formed inside dark matter halos, with smaller systems appearing first and larger structures assembling over time, is less than has sown. 5 is greater than later cosmic acceleration is described by the lambda part of the model, which stands in for dark energy. It is a remarkably economical framework, and it has been very successful in describing major observations such as the cosmic microwave background and the large-scale structure of the universe. It would be far too simplistic to say that because Webb has revealed a few uncomfortable early systems, everything in cosmology is broken. That is not how serious science works. Lambda CDM remains a powerful model because it explains a wide range of observations very well, including the cosmic microwave background and the broad pattern of structure growth across the universe. Even researchers who focus on Webb-era tensions often begin by acknowledging how successful the standard picture has been on large scales. And still, a strong model is most revealing where it begins to strain. That is where the present moment becomes so interesting. Not because cosmology is collapsing, but because one of its most successful frameworks is being tested in one of the hardest places to test it, the very early universe. And that is where the tension seems to gather. In the earliest galaxies, in the earliest black holes, in systems that look too bright, too massive, too structured, or too active for their place on the timeline. Webb has given astronomers a much richer view of the early universe than we had before, and with that sharper view has come a more serious discussion about whether some high redshift galaxies and black hole candidates are maturing faster than the simplest expectations would suggest. And the difficulty has a very specific shape. The issue is not that lambda CDM somehow forbids galaxies, or black holes, or quasars. Of course it does not. The issue is narrower than that, and more interesting. Some of the earliest structures appear, at least in certain cases, more mature or more efficient than the simplest timetable would lead us to expect. So the tension is not really about whether such objects can exist. It is about how soon they seem to appear. Not existence, but chronology. We are trying to understand which part of the standard story may be too simple at the earliest times. Is the main issue the size of the first black hole seeds? Their growth rates? The formation of halos? The way we translate faint, observed light into estimates of mass? Or does the tension reach even further back into the initial conditions of the universe itself? Lambda CDM is not a weak idea held together by optimism. It is a powerful and well-tested cosmological framework, is less than Hasson. 5# is greater than 2c. But Webb-era observations have drawn attention to one part of the story where the tension becomes especially important. The first few 100 million years, when some galaxies and black hole systems seem more developed than expected. So the real question is not whether the model fails everywhere. The question is whether something important happens at the earliest edge of structure formation that the simplest version of the model does not yet capture clearly enough. So now, we can begin looking at the main places where that missing piece might be hiding. One possibility involves the behavior of dark matter. In the standard picture, cold dark matter provides the invisible gravitational framework inside which galaxies form. And if that framework behaved differently in the early universe, then the timing of structure formation could shift as well. If dark matter clustered differently, interacted differently, or helped create earlier and denser collapse under some new mechanism, then the first halos and the first environments where black holes could grow might have formed sooner than expected. That is why some researchers have explored non-standard dark matter ideas in the first place. Very early supermassive black holes are difficult to build in the simplest ordinary scenarios. Another possibility lies even earlier, in the initial fluctuation pattern of the universe itself. The standard story begins with tiny primordial irregularities, but the exact distribution of those irregularities matters enormously. If slightly more structure was present on certain scales, or if rare high-density peaks were more effective than the cleanest average picture suggests, then the first gravitational wells could have appeared sooner and deepened more quickly. That would not overturn the idea of structure formation. It would mean that its earliest stages began from slightly different starting conditions than we often assume. Imagine rainwater spreading across a landscape. If the land begins almost perfectly flat, water gathers slowly. But if the ground already contains slightly deeper grooves, streams begin to organize much sooner. In cosmology, the primordial fluctuation spectrum plays a similar role. It sets the initial unevenness of the terrain. And tiny differences there can lead to very large consequences later, affecting when the first halos, the first galaxies, and perhaps the first giant black holes appear. A third possibility is less dramatic, but just as important. Some of the tension may come not from new physics, but from interpretation. Early Webb candidates are faint, distant, and difficult to analyze. Their inferred masses depend on modeling. The translation from observed light to stellar content is not always straightforward, is less than Hasson. 5' is greater than dust, active nuclei, and unresolved structure can all complicate what first looks like a simple galaxy measurement. That does not make the tension disappear. But it does remind us that at the frontier of observation, what we see and what we infer are not always the same thing. And beyond all of that, there is still the possibility that the missing piece is something deeper. Not necessarily that the standard cosmological model must be thrown away, but that it may need an extension, a correction, or a part of the story we have not fully understood yet. Perhaps the earliest collapse physics worked differently than we usually picture it. Perhaps black hole seeds had access to channels we do not yet fully account for. Perhaps the dark sector behaved in richer ways than the simplest cold dark matter picture assumes. Or perhaps the first few 100 million years of the universe were simply less orderly, more efficient, or more uneven than the neatest summaries make them seem. So the pressure on cosmology may be coming from more than one place at once. It may involve dark matter behavior. It may involve the primordial fluctuation pattern. It may involve the physics of black hole seeds, unusually rapid feeding, or the way we infer mass and activity from faint early signals. And that is exactly why this tension is scientifically useful. It does not force one dramatic conclusion. It forces better questions. Science is not being embarrassed by this moment. it is being refined by it. A strong model is being asked to explain observations from a part of cosmic history that used to be dim, distant, and hard to test directly. Webb did not break cosmology. It brought cosmology into closer contact with the earliest universe than ever before. And there is something remarkable in that. For a long time, the opening chapters of cosmic history were known mostly through inference and extrapolation. Now they are becoming a place where theory and direct observation can meet much more closely. And when that happens, two outcomes are usually possible. Either the old framework survives and becomes even stronger because the tension softens under better interpretation, or the old framework survives in a revised form because it must absorb something real that it had not yet captured. In either case, that is not failure. That is what scientific progress often looks like. The universe gives us a harder question, and our models are forced to become more precise. The black hole at the center of this story may indeed be the most powerful sustained engine in the universe. But it may also be something more than that. A clue. A sign that the early universe may not have unfolded quite as gently as we once imagined. Did we discover the most powerful object in the universe? Or did we uncover one of the clearest hints that the universe had a very different early life than we once thought? By now, the black hole has changed in front of us more than once. At first, it seemed like a dark and misunderstood object. Then it became an engine. Then a regulator. Then a possible challenge to the timetable of cosmic history. And now one more shift begins to appear. The most powerful object in the universe may not be only an astrophysical phenomenon. It may also reflect something about us. A mirror of what? Of the way human beings build confidence in their explanations. Of the way we turn patterns into stories. Of the way elegant models can feel complete, right up until nature shows us where they are still unfinished. And if we are careful, that correction does not weaken science. It deepens it. Take a moment and step back from the black holes themselves. Because what happened here is remarkable in its own right. A species on a small rocky planet, orbiting an ordinary star in one outer region of one galaxy, decided that it wanted to understand how the universe first began building structure. Not just as a story, not just as an idea, but as something that could actually be measured and observed. So we built a telescope of extraordinary precision. We folded it into a rocket. We sent it far from Earth. We placed it in deep space, where it could stay cold, stable, and quiet enough to do its work. And then we asked it to catch light that began its journey long before our planet looked anything like it does now. That alone is worth pausing over. Because this is not only a story about distant black holes. It is also a story about the fact that the universe can be studied at all, and that we have become capable of listening to it with instruments delicate enough to reach that far back. And if we are honest, we expected a fair amount of confirmation. not because scientists are blindly confident, but because strong models earn trust over time. The standard cosmological picture has explained a great deal. It has earned the right to be taken seriously. So when Webb turned toward the deep past, it was natural to expect that the early universe would broadly fit the outline we had already built. But in some parts of the data, that is not quite what happened. What came back was not total contradiction, but tension. Not chaos. Not the collapse of science. Just tension. The kind that tells you a picture may still be missing a few important pieces. Because that is often how reality corrects us, is less than her own. 5# is greater than it does not always tear a theory apart. Sometimes it simply presses against the places where the theory is still too smooth, or too neat, or too confident in its earliest chapter. The problem is not only that these objects exist, it is that some of them seem to appear early enough to reveal assumptions we may not have realized we were making. Human beings built an instrument and placed it far from Earth to catch ancient light. And reasonably enough, we expected that nature would broadly support our best account of early cosmic growth. Instead, we found hints of systems that may have matured faster than expected. That tension is not a disaster. More often than not, tension in science is where deeper understanding begins. And that distinction matters. People are often taught to think of science as a machine for producing certainty. But at its best, science is not really a machine for protecting certainty. It is a method for testing it, revising it, and sometimes letting go of the parts that no longer hold. The black hole at the center of a young galaxy is not just a source of radiation, gravity, and feedback. It also becomes part of the story of how human understanding works. It reminds us that even strong models, elegant models, successful models can still be incomplete. Nature does not have to fit perfectly inside our cleanest summaries. And that is not a weakness in science. It is one of its strengths. A weak method hides from contradiction. A weak method treats tension as embarrassment. But science, when it is working well, treats tension as information. Not every anomaly survives. Not every surprise becomes a revolution. Some tensions weaken as the data improves. Some fade when the models become more careful. But even then, something valuable has happened. The model has been tested, and our confidence has become more honest. That is one reason the black hole starts to feel like a mirror in this story. It reflects back not only extreme physics, but the current limits of our understanding. When we treated it mainly as a monster, it revealed our attraction to spectacle. When we understood it as an engine, it revealed how far explanation could take us. And when it appeared too early, too active, or too mature for our expectations, it showed us how cautious we need to be when telling the story of the past. The early universe asks for a certain kind of humility. Not the humility of giving up, but the humility of keeping our scale in mind. We are clever, yes. But we arrived late. The light Webb collects left its sources billions of years before our species existed, is less than her own, 5# is greater than. Those ancient systems were already forming, colliding, radiating, and perhaps activating supermassive black holes, long before there were observers here to wonder about them. And yet, here we are. We can reconstruct. We can argue. We can revise. And there is something deeply moving in that. We are small, yes, but not irrelevant. We arrived late, but not too late to understand something real about where we came from. That is why this discovery is not only about distant violence. Violence is the easiest part to notice. A quasar is bright. A black hole is extreme. Jets and accretion disks are dramatic. But the deeper meaning lies elsewhere. It lies in what these objects force us to reconsider. They make us look again at origins, at timing, at what we really mean when we say something appeared early or matured quickly. And they make us notice how many hidden assumptions can live inside even our most refined cosmological stories. In that sense, the greatest power in this story may not be energy release alone. It may also be the power to reorganize how we think. The power to bring theory, observation, and imagination back together under stricter conditions. The power to remind us that history, even cosmic history, is never understood once and for all. So, the most powerful object in this story turns out to be powerful in more than one way. It does not only dominate matter, it also forces us to revisit some of our deepest assumptions about the early universe. And that tension is valuable. It pushes our explanations to become more careful, more flexible, and more honest. We expected confirmation. Instead, we found a challenge. And that challenge reminds us that the universe is still larger than our cleanest summaries of it. There is a common temptation to think that understanding reduces wonder. But science usually teaches the opposite. Superficial wonder depends on vagueness. Real wonder survives detail. In fact, it often grows stronger because of detail. The more clearly we understand what it takes to build a supermassive black hole, the more striking it becomes when one seems to appear too soon. The more carefully we understand the usual cosmological timeline, the more meaningful the tension becomes when the early universe seems to move faster than expected. This was never really just about picking a winner among extreme objects. It became something else. A way of following what power actually means, all the way to its edges. We started with brightness, then gravity, then influence, consequence, and slowly something deeper began to appear. Because by the time we reach this point, the answer no longer feels quite the way we expected. The most powerful object is not only the one that dominates matter, it is also the one that changes how we think about the story itself. So where does that leave us? Not in confusion, not in despair, but in a better place than either of those. A place of sharper attention. The universe has not become less intelligible. It has become more demanding. And perhaps that is one of the clearest signs that we are dealing with something real. We built a telescope to look back in time. What we found was not only ancient light, but also a challenge to our confidence. And that challenge matters precisely because it comes from reality, not from rhetoric. It reminds us that even our best models are still models. They can be powerful. They can be beautiful. They can be extraordinarily accurate. But they are never the universe itself. We have traveled a long way to answer what first sounded like a simple question. What is the most powerful object in the universe? By now, that question no longer feels simple, and that is a good thing. The universe rarely rewards the first version of a question. It rewards the patient version. The version that has been tested by definitions, comparisons, equations, tension, and doubt. So now, as we come closer to the end, the answer should probably be said plainly. Not in the language of a headline, and not as something oversized for effect. Just as a conclusion we have arrived at slowly, one step at a time. If by most powerful we mean the strongest magnetic field, then the answer points to the magnetar. In that category, it gives us one of the most extreme electromagnetic environments known in nature. If by most powerful we mean the most violent brief outburst, then the answer points toward the gamma-ray burst. Over short timescales, very few known phenomena can match that level of intensity. If by most powerful we mean the deepest gravitational trap, then the answer is the black hole itself. No other known object curves space-time so strongly that beyond a certain boundary, escape is no longer possible. But if by most powerful we mean the brightest sustained engine in the cosmos, one that can do more than release enormous energy, one that can also influence gas, star formation, and the future of an entire galaxy, then the answer becomes much more specific. It is the quasar. More precisely, it is the actively feeding supermassive black hole in its quasar phase. And that is the strongest answer to the title of this documentary, is less than ℏ. 5 is greater than. The most powerful object we have found is the actively feeding supermassive black hole, seen at its brightest as a quasar. What makes that answer so striking is that it is not the most obvious kind of answer. We did not end with the largest thing in a simple geometric sense. We did not end with the loudest single explosion. We ended with a system in which gravity, motion, heat, radiation, feedback, and time all work together to produce something far more consequential than spectacle alone. A quasar is not just bright. It is bright because matter, falling into an extremely deep gravitational well, can turn that fall into radiant power with remarkable efficiency. It is not just compact. It is compact and yet able, through jets, winds, and radiation, to affect conditions across distances vastly larger than itself. And it is not just an object sitting in the center of a galaxy. Under the right conditions, it can influence whether that galaxy keeps forming stars, whether its gas remains cool enough to collapse, and whether its future is active or quiet. That is why this answer feels different from the others. A magnetar is extreme in magnetism. A gamma-ray burst is extreme in brief violence. A black hole is extreme in gravity. But a quasar brings several forms of power together into one long-lived system. It combines brightness, gravitational authority, and large-scale influence in a way few other objects can. The magnetar may be the strongest candidate for magnetic extremity. The gamma-ray burst may be the strongest candidate for a brief blast of violence. The black hole may be the strongest candidate for pure gravitational trapping. But the best answer to the title of this documentary, the most powerful sustained object we have found in the universe, is the actively feeding supermassive black hole in its quasar phase. And even that is not the end of why it matters. Because this object does something that few others can do. It does not only dominate matter, it also changes the questions we ask. It reaches beyond astrophysics and into cosmology. It forces us to ask not only what it is, but how it formed, when it formed, and whether the universe should have been able to build it so early. It is dark, and yet it can create some of the brightest sustained beacons in the universe. It is compact, and yet it can influence the life of a galaxy. It may have become active earlier than our most comfortable timelines would have expected. And by trying to understand it, we may be pushed to revise part of the story of how cosmic structure first grew. That may be the deepest reason this story stays with us. The quasar is not just the winner of a comparison between extreme objects, is less than Hasson, 5# is greater than. It is also a reminder that the universe does not have to follow the neatest version of our expectations. Some discoveries do more than fill in missing details. They force us to reconsider the order in which those details were supposed to appear. And if that feels unsettling, that is understandable. But it should also feel hopeful. Science does not become weaker when its questions become sharper. It becomes more alive. Again and again, some of the most important advances in physics have come not when nature matched our expectations perfectly, but when it asked more of us than we were expecting. The most powerful object in the universe is not only powerful because of what it does to gas and light. In a quieter way, it also changes how we think. It sits at the meeting point of gravity, heat, galaxy evolution, and cosmic history, and it pulls all of them into the same conversation. That is a rare kind of power. The power to radiate, the power to shape, and, slowly, the power to make us rethink what we thought we understood. So the answer can now be said simply: The most powerful object we have found is the actively feeding supermassive black hole, seen at its brightest as a quasar. Not because it dominates every single category, but because it brings several of the most important ones together: immense energy release, deep gravitational control, long-term influence over a galaxy, and a quiet pressure on our understanding of the early universe itself. And perhaps that is the most fitting way to end. We began by asking about the universe's greatest engine. But along the way, that engine became something more. Not just a source of power, but a kind of teacher. A dark center that makes galaxies blaze. A compact abyss that can shape an entire cosmic city. A distant light from the early universe, still asking us, quietly, whether our story of beginnings is complete. As Subramanian Chandrasekhar once reflected, in some strange sense, science is a picture of the universe translated into the language of man. And here, at the edge of that translation, it feels as though a few of the most important sentences are still being written. So we keep listening. We keep refining. And we keep looking deeper into the dark. Because sometimes, that is where the brightest answers are waiting. Thank you for being here. And until next time, good night.